Alright, welcome back to section 4.2. I'm going to do an example. So we have f of x equal to x times the square root of 4 minus x squared on the interval minus 2 to 2. So we're asked to find the critical points of f, then we're asked to find, or to use the first derivative test to locate the local max and min values. And then we're asked to identify the absolute min and max values on the given interval. Alright, so for part A, we want to locate the critical points. We find the critical points by taking the first derivative and setting the first derivative equal to 0, finding what x values satisfy that equality, and then we also look for any points that are undefined in the first derivative. So let's start off by finding f prime of x. I'll use the product rule here. So f prime of x is equal to x times the derivative of root 4 minus x squared, which is 1/2, times 4 minus x squared to the negative 1/2, times minus 2x. So we're using the chain rule here, and then we use the product rule. So the first times the derivative of the second, plus the second, times the derivative of the first. The derivative of x is just 1. Let's clean this up a little bit. The 1/2 and the 2, 1/2 times 2 is 1, so we can go ahead and simplify that a little bit. And we're left with, let's see, minus x squared all over root 4 minus x squared plus root 4 minus x squared. And again, we're looking for critical points, so we set this equal to 0. And now we're solving this equation for x. A couple ways to proceed. I think what I'm going to do is get a common denominator of the root 4 minus x squared. So I'm going to multiply the second term by root 4 minus x squared over root 4 minus x squared. It's going to give me minus x squared plus 4 minus x squared all over radical 4 minus x squared. And we're solving that for 0. Now I'm going to go ahead and try to clean up the numerator a little bit. I'm going to go to the next page. We've got 4 minus 2x squared all over the square root of 4 minus x squared. Try to clean that up. Equal to 0. So this equation, this expression is going to equal 0 when the numerator equals 0. So when 4 minus 2x squared equals 0. Solving this for x, we get that 2x squared equals 4, so x squared equals 2. X equals plus or minus root 2. So plus or minus root 2 is indeed in our given interval. Remember, we were asked to look at the interval from minus 2 to 2. And then we also want to look for any points in the interval where the function's undefined. It actually is going to be undefined at the endpoints of the interval minus 2 and 2. So we'll go ahead and make a note of those, even though they aren't interior points to the interval. But just note that whenever this denominator is 0, we're going to have some problems. So x can't equal plus or minus 2. And okay, so we found our critical points. Part B, if we go back a page here, Part B is asking us to use the first derivative test to locate the local maximum and minimum values. So the first derivative test wants us to examine the behavior of the first derivative around critical points. So we need to figure out where is the first derivative increasing and where is it decreasing. So I'm going to draw a chart here. I'm going to draw a plus-minus chart. And this is just a number line. I'm going to indicate our critical values. Remember, we're only really looking at values between minus 2 and 2. Hopefully you've noticed, or at least notice now, our function, if I go back, our function doesn't exist outside of the interval minus 2 to 2. We've got that radical root 4 minus x squared. So it's only going to exist on minus 2 to 2. Okay. So here I am indicating minus 2 minus root 2 plus root 2 and 2. And I'm going to test some values. So again, our function doesn't exist to the left of minus 2 or to the right of 2, so I don't need to test values on either sides of those. They're also outside of the given interval. So I'm going to pick values between minus 2 and minus root 2, between minus root 2 and root 2, and between root 2 and 2, and see what the sign of the first derivative is. Okay, so here I'm checking the sign of f prime of x. Alright, so on this first interval here, I'm going to test f prime of negative 1.5. Okay, that's in that interval. And if I plug negative 1.5 into my derivative, it turns out that I get negative 1/2 over root 7 over 2. We don't necessarily care what the value is here, we're just looking for the sign. So it's a negative. So that tells me that the first derivative is decreasing on the interval minus 2 to minus root 2. We've got a critical value at minus root 2. Now we pick a point between minus root 2 and root 2. So I'm going to pick 0. So f prime of 0 is equal to 4 over root 4. I mean, I could simplify that, but again, I'm just looking for the sign. And so you can see that the sign here is positive. So that indicates that the function is increasing between minus root 2 and root 2. And then lastly, I'm going to test a point between root 2 and 2. So I'll pick 1.5 or 3/2. So f prime of 3/2. If we plug that in, that comes out to be minus 1/2 over root 7 over 2, which is a negative number. So that tells us that our function is decreasing from root 2 to 2. So, what does that mean? Well, if we look at the critical point minus root 2, since our function is decreasing and then increasing, we have behavior like this. So that means at negative root 2, we have to have a local minimum. And similarly, the first derivative test tells us what's happening around root 2, our other critical point. Okay, so to the left of root 2, we have an increasing function, whereas to the right of root 2, we have a decreasing function. So that tells us that at root 2, there has to be a local maximum. Okay, so let me write that up. So therefore, there is a local minimum at x equal to minus root 2 and a local maximum at x equal to root 2. And the last part of this problem is to identify the absolute minimum and absolute maximum on the given interval. So this goes back to the extreme value theorem that we talked about in the last section. So to identify the extreme values on a closed interval, we look at the function values at each of the endpoints of the interval. And we're looking at the function values here. Okay, so we're plugging minus 2 and 2 into our function. And we're also going to be plugging in the values of our critical points and seeing what the function value is at the critical points. And that's going to give us the extreme values. So I did this ahead of time and plugged all these values in. So f of minus 2 is 0, f of 2 is 0, f of minus root 2 comes out to be minus 2, and f of root 2 comes out to be 2. So that tells us that at minus root 2, we have an absolute minimum. At root 2, we have an absolute maximum. Alright, so I hope this section goes well. Let me know if you have any questions on anything.